Hello. In today's presentation, I will be reviewing the paper Spectre Attacks on Exploiting Speculative Execution, which was released in 2019 IEEE Security and Privacy Conference by Paul Kosher and others. So, the big question is, have performance gains undermined security over the years? Industry research and development and market share focus on improving performance of processors, and they have done so historically. For the past 45 years, the entire focus of the industry has been on how to make the processors even more fast and more performance intensive. But in doing so, they have made the architectural state so ambiguous that it opens gateways for many security vulnerabilities. In this paper, uh, the authors have exploited the use of caches and speculative execution. Caches are generally used to reduce memory latency, whereas speculative execution allows out of order execution. These two are the pillars of modern performance gains in computer architecture. So this paper shows how these two fundamental performance concepts in computer architecture can be exploited to reveal sensitive information. So talking about speculative execution, what is it really about? So at the heart of speculative execution lies branch prediction. It basically guesses if a branch will be taken and executes the program under the assumption that whatever the assumption is, whether the branch will be taken or not taken. So, for example, there could be a possibility where, uh, like, it takes data time to be fetched from memory. So, to like not waste the time between the delay in fetching data from memory, modern processors use this concept of speculative execution, which basically uh, executes a branch and then stores that data in some buffer. And if that data if the branch is later on found to be not to be taken in the real program, then that data will be flushed. But if that branch is indeed to be taken, then that data uh, is already present in the cache and it saves a lot of time. So, in summary, if the assumptions match the results, execution continues as normal. If the assumptions and result differ, the progress is thrown out and execution starts from where the assumption was made. And all this is done by using a branch trainer. So it basically uses previous branches to predict the future branches. And now we will use all of this information to explain the attack. Can speculative execution be exploited? As you can see in the figure, there are four possible cases of out of bounds check in a processor. What could happen? In general, the key concept of Spectre attacks can be explained by this picture. If some the Spectre attacks induces errors to create faults and exploits the transient nature of instruction execution to create a covert side channel. So what does this mean? It means that we are forcing the branch predictor to mispredict a branch, and this branch will be speculatively executed under the assumption that it is true. Using this error that we have created and the transient execution of this instruction while the branch is being resolved, we open up a small window to access sensitive information from the memory. So uh, here another fundamental concept which we will look into would be utilizing fast cache access times versus latency of data acquisition from memory. So let's get down to how Spectre works. Spectre variant 1 conditional branch. This is the first variant that was ever found, and it's really interesting. So uh, the threat model assumes that the code runs in a trusted environment. As you can see in the figure, the attacker can control the variable X. Branch prediction is mistrained to take conditional if branch before inserting the malicious X. So the branch predictor will assume that the branch must be taken, and it would hence execute the malicious lines of code which would give us access to the sensitive data in the memory. So another assumption is that array 1 size and array 2 are not present in cache. Some secret out of bounds values of array 1x are present in the cache, leading to a cache hit. And so we will utilize this for our attack. Um, so this is how it works in theory. An attacker mistrains the branch if to predict true, to take the branch. Then the attacker calls the victim code with malicious X, which is out of bounds. So say the array 1 size is 8, but the attacker would mistrain the branch predictor by giving it values of X, feeding it values of X within the range of 0 to 8. And this way, like eventually, when it is the time to actually access some sensitive information, the attacker would then send this mistrained branch predictor the value of X, which could be out of bounds, say something much, much bigger than 8. So this way, we could access data outside the array 1X, which lies in the memory, and the attacker would have the secret key. Next, a read of array 1x is made, which and hence array 1x, the secret value already resides in the cache. This was our assumption. There is a cache hit, and we quickly get that data. Now, the next instruction is executed, which is a fetch request for array 2 uh, value uh, at the secret value would be executed. And since array 2 was not in the cache, this would take some time to fetch from the memory. And meanwhile, when it is being fetched from memory, it might happen that the branch prediction is finally resolved and the branch is hence flushed. But the cache already has the value of array 2 at pointed to at the secret key. So the attacker could then use this address location in array 2 by using some kind of flush plus reload or some other cache timing attack to reveal the secret keys. So this is how the Spectre variant 1 attack works in theory. Now I will talk about Spectre variant 2, which is indirect branch misprediction. So what happens here? So this attack takes inspiration from return-oriented programming, where the only difference is that in this variant, the attacker chooses a gadget from the victim's address space and influences the victim to speculatively execute the gadget. But unlike return-oriented programming, the attacker does not rely on a vulnerability in the victim code. Instead, the attacker trains the branch target buffer to mispredict a branch from an indirect branch instruction to the address of the gadget. This results in speculative execution of the gadget. Then, this Spectre gadget, which is a code fragment that transfers sensitive information into a covert channel, is executed. All this is done by training the branch predictor to mispredict in order to execute the Spectre gadget, as can be seen in the figure. Uh, so there are also other kinds of Spectre vulnerabilities. Since Spectre is a very core fundamental vulnerability which exploits speculative execution and cache timing attacks, it is uh, it is fundamentally present in almost every modern computing system you can imagine. So there are many different ways this vulnerability could be exploited if the key idea behind the vulnerability is taken into mind, which is that the attacker needs to create a speculation scenario that the uh, underlying computer architecture needs to have a speculation scenario which would lead to a computation error, and that safe computation can be turned into unsafe by using speculation. That this finally creates a window of opportunity, which creates a side channel which could be exploited by an attacker to leak data. And so there could be many variants like Spectre RSB, which is return stack buffer. Uh, so Spectre RSB relies fundamentally on using mistrained returns. What happens is, so there is a return stack buffer inside the computer architecture state, and which stores the return addresses of function calls and stuff like that. So this is generally done so that during speculative execution, it could speculatively return control and continue execution without wasting time. But an adversary could uh, so the return address is stored in two locations. It is stored in the return stack buffer and it is stored in the stack, the software stack of the program. And how the branch is finally resolved is that the address which is stored in the software stack is compared. So until the address stored in the stack is available to the program, to the computing system, the return address from the return stack buffer is used by the hardware architecture state for speculative execution. Now, an attacker could actually pop the return address from the software state, but that return address could still exist inside the return stack buffer. This way, he's able to induce an error in the speculation scenario and use that speculative window to access data from the memory and leak the secret data. So there is another variant of attack red to spec, which is kind of similar to that, Spectre 1.1, Net Spectre, Spectre V4, and there are like many others besides these, which you could look up. So in summary, uh, yep, sorry, I missed the slide. So a Spectre class of vulnerability is defendable in the real world scenario. So about this, the paper offers some mitigation strategies which are really interesting, but they do not come without some trade-offs. So I'll be talking about that. The first is preventing speculative execution. This method greatly reduces performance unless there is some modifying software present, such as preventing speculative instructions or inserting L-fence before indirect branches to ensure pipeline clear and reduce instructions that can poison a branch. But care should be taken that not too many L-fence instructions are inserted because it is very computing heavy and it would greatly reduce the performance of the processor. Another mitigation strategy which was proposed is preventing access to secret data. Sep so, like, one of the key concepts here is process isolation. There could be separate permissions so that attacker can only access limited information even if he or she is successful. This is pretty common in Google Chrome, which runs each website on a separate process. Another way this could be done is replacing array bounds out of bounds check with index masking, which will ensure if the index is far larger than array size. This may allow access outside of array, not by preventing data that can be accessed, which means that it does not actually have a bounds check. It does not perform a bounds check, but it does not allow the index to be greater than 8. Finally, like we could protect pointers by XORing them with pseudo-random poison values. This prevents attackers from using poisoned pointers. Next, another mitigation strategy is preventing data from entering covert channels. So this could be done by detection of data fetched, which was used in speculative operation, and prevent data from being used in subsequent operations that may cause a leak. But the current computer architectures, the current processors are incapable of doing this. So something like food for thought for future microprocessor designs. Another mitigation strategy is limiting data extraction from covert channels. Spectre attacks rely on covert communication channels, where the goal is to mitigate such channels by limiting shared array buffers. Uh, Again, current processors are incapable of performing this in its entirety, but this could this is something interesting which could be researched on. Finally, the last mitigation strategy mentioned in the paper was preventing branch poisoning. So, how this works is that the instruction set architecture was extended to include mechanisms to control indirect branches. Indirect branch restricted speculation is a strategy where branches in less privileged code cannot affect indirect branches in higher privilege. Another strategy is single thread indirect branch prediction, where branch prediction is no longer shared between hyperthreads. Indirect branch predictor barrier places a barrier between software that separates branch prediction, like flushing the branch target buffer or something like that. And finally, the recto lines, which is return to trampoline. And this is again used by Google, which replaces indirect branches with return statements and has the branch predictor go into an infinite loop of predictions in case of misspeculation. So these are some interesting mitigation techniques which could be thought about. In summary, the contributions that this paper uh, does is are follows. It reveals a vulnerability using maliciously incorrect branch predictions to reveal sensitive data through side channels known as Spectre attacks. It shows other variations of Spectre attacks, which are common in the microprocessors that are present today, and all of them use timing and malicious branch prediction. It demonstrates how to manipulate different branch predictors. It offers potential mitigation strategies to Spectre attacks, and it also discusses many performance enhancing features which sacrifice security. And it suggests that any long term solution will require a fundamental change to instruction set architectures and the thinking of the big dominant powers in the industry, which would force design in this direction where security is prioritized over performance. Uh, so, in summary, the paper is about accessing secret information using speculative execution, which is code which is executed but not committed due to branch predictors. Now, so in conclusion, there has been a shift of focus in hardware software core design in the recent years. So, around 30 years ago, all the big players in the industry really focused on performance, legacy compatibility, and stuff like that. And because at that time, the security issues, the security vulnerabilities were not so glaring, so everyone thought that it would be important to work on performance to improve performance for uh, the future computing paradigms, which was kind of reasonable, but it doesn't work in today's scenario where the modern microprocessors are like highly competent in terms of performance and they can execute many different kinds of code, many high power intensive and performance intensive codes, but these processors are still vulnerable to a host of security vulnerabilities, and the ambiguity which has been introduced in these systems because of their enhanced performance is the prime cause of why there are such gaping security holes in today's microprocessors. So, one, there is a very important call to specialized designs for performance versus security trade space. You can see in the picture below. Uh, It is important to design TCBs which and design processors which have this kind of compatibility where the programmer or the end user can decide for himself where he wants to prioritize performance and where he wants to prioritize security. So the processor could provide both like two sets of architectures where one could be highly performance intensive but not so secure, and another where the processor is slightly slower, you could say, but like highly secure. So depending on the application of the end user, this capability finally ends up in the hands of the user, and it would be really beneficial for a lot of people. So this was my talk. In conclusion, it would be great if you guys would check out this paper, and it's really interesting. It is one of the biggest security vulnerabilities which have been uncovered this in this decade, and I highly recommend it. So, thank you.